Hello everyone, this is Dr. Young, and in this video we will be talking about directing groups or directors. And that will have to do with, if you have an aromatic ring that already has a group on it, how is that going to direct the electrophile into a certain spot on that aromatic ring? So like for example, right, we have done iodinations. I just picked iodination to have something. And we said, okay, well you can just draw this aromatic ring. And I can put an iodine wherever, right? Because this is the exact same thing as putting the iodine up top, right? I just rotated it slightly. So it doesn't really matter where I put the iodine. Now, if there's already a group on there, like this methyl group, now it does matter, right? So now if I have a CH3, this is not the same thing as this, which is not the same thing as this. So we need to ask ourselves, well, if I can get three different products here, and I didn't draw a fourth and fifth, right? Because if I put the iodine over here, that's the same molecule. And if I put the iodine over here, that's the same molecule. So these are really the only three options. So the question becomes, well, which one of these then is going to be the product that I form, right? And you may remember from the naming stuff that this is considered an ortho relationship and a meta relationship and a para relationship. So which one is going to be the major product? And for example, what we need to talk about is that when you do this particular reaction with this particular one, we don't tend to see a lot of meta. We tend to see ortho and para. And so how do I know that? How do I know that a methyl group is going to have groups that are more ortho and more para, but not meta? That's what this video is all about. So what we're going to do is we're going to make a chart. I'm going to reintroduce this chart here. We've already talked about the activators and deactivators, the strong and weak ones, in a previous video, but we're going to use the same table to organize our directors. What things are meta directors, what things are ortho-para directors. So I just want to go over this real quickly with you to remind you, right, that the strong activating groups are things with lone pairs. So we're talking like an OH or a OCH3, any sort of ether group or nitrogen groups. Whatever it happens to be, as long as it has a lone pair at that point of attachment, then that's what we're talking about. Those are the strong activators. We also said that the weak weak activators were the alkyl groups, right? So that's just your generic R group. So it can be anything from like a methyl to like some long chain thing attached to your aromatic ring. Doesn't matter. And then our strong deactivators, right? We said that those were things that had pi bonds. So like a nitro group would be a good example because it has a pi bond and a positive charge. Or our acyl groups, so whatever this would be, maybe it's an ester or a ketone or whatever. Or anything that full on has a positive charge at that. So that'd be a lot of like the quaternary ammonium salts. So this would be NH3, and there would be a positive here. Or something with at least a very large positive charge. So like CF3 would be very withdrawing because that carbon is very positive because of those three fluorines. And then the last group was the halogens. So we're going to look at a member of each of these four groups here and ask ourselves, how do they direct? Are they going to be ortho-para directors? Are they going to be meta directors? And then what I'm going to do is after we talk about those four, I will show you this table again and we will add on to it, oh, hey, strong activators are ortho-para directors or something like that. So let's take a look at a strong activator, right? So something with a lone pair, right? So these have a lone pair at the point of attachment. And just to emphasize this, when I'm talking about the point of attachment, I mean it's attached to the aromatic ring. So something like this would not count, right? Because the lone pair is way out here. The lone pair is not on the ring. It cannot donate electrons into the ring, right? All of these are sp3 hybridized. There is no conjugation. There is no overlapping p orbitals that go between the nitrogen and this aromatic ring. So this is not what I'm talking about, right? We're talking about the point of attachment, which is this sucker over here. And there's different ways you can look at the rationale behind these. I'm going to provide the best ways that I can think of for students, right? I'm definitely taking a more teachery, instructionally point of view from this. So if I take a look at this nitrogen, right, we said that these electrons, can drop down. And that puts the electrons there. Now that's going to give me a series of resonance structures, and I am going to draw all of these out to make my point. And remember that because of these resonance structures, right, we said that the nitrogen is a strong activating group, right, because it donates electrons into the aromatic ring. Right, yeah. So yeah, they have lone pairs, they can be electron donors. Anyways, so I can keep moving this lone pair around like this, so I can get another resonance structure, where now the lone pair is at the bottom. And I can do one more where I move the lone pair to a pi bond right here, and then these kick up. And those are all my resonance contributors. Now, the importance here, right, is that the real structure should look something more like this, right? Where I've got the NH2. For the most part, the lone pair is there, and then we know that the resonance structure means that the pi bonds are located everywhere. But what this is saying is that I'm going to start building up a positive charge on the nitrogen because the lone pairs get put into the aromatic system. And this spot gets a little negative, and this spot gets a little negative, and this spot gets a little negative, right? Because I have one resonance contributor where the negative is in that ortho position, one away, that's this. I have one where it's opposite of the nitrogen, that's the para position, that's this. And I have one in the other ortho position, which is this. And that's going to be helpful, right, when I'm asking myself, well, will this be attracted to an electrophile? Right, so where on this ring is it going to be attracted to an electrophile? Hopefully you see, right, that the electrophile should be attracted to the negative spots. Right, so what we can say here is that for these types of molecules where you have a lone pair at that point of attachment, you can say that the electrophile is attracted to the ortho, right, which is this position right here, which is, well, I'll highlight that in a second, the ortho and para positions. Right, and if you don't remember this from the videos, the ortho positions are right next to the group you're talking about. And then the para positions, the para position is the one opposite of the group that you're talking about. So my electrophile, since it's positive, is going to be attracted to the negative spot. So let's take a look at one of these strong deactivators, like an acyl group, for example. So here we have a ketone attached. It's a similar but opposite story, right? We said that these were strong deactivators because electrons could come out of the ring and go into the group. So I'll get a resonance structure like this, and then I'll move the positive charge over to there. Draw the rest of this. And then we can move the positive charge one more time to get into the last position. And these would be the resonance structures for this molecule. And again, right, the real molecule then must look like a blend of all of these. Mostly looks like the carbonyl is still there, but we can see from the resonance structures that the oxygen is starting to get partially negative. This ortho position is starting to get partially positive. The para position is starting to get partially positive, and the other ortho is also. Now, again, we are talking about being attracted to an electrophile. And so now the ortho and para positions are positive. Remember in the previous one, they were negative. So now the idea is that the electrophile is repelled from those ortho and para positions. Which means then that the electrophile is going to go to the meta position. Right? It's better for it to go to the meta position because at least it's not being repelled from there. So we're going to end up seeing the alkene from these meta positions go pick up the electrophile. So all those strong deactivators, they tend to be meta directors. Now I've got a chlorine here. I'm actually not going to do this whole one with the chlorine because as you can see, it also has a lone pair. So it's also going to be like that one, the NH2 one, where these electrons drop down, these kick out, you get a resonance structure here, where you have a negative charge, double bond Cl. That's positive. You can imagine it's a pretty minor contributor. And I'm not going to draw all the resonance structures because it's the same thing as before, where we see that overall, because of the delocalization, because of these resonance structures, the chlorine gets partially positive, the ortho spot gets negative, the para spot gets negative, and the other ortho spot gets negative. So then there is an attraction to these ortho and para positions. This is the exact same thing, right? It has a lone pair on that point of attachment. So also is an ortho para director. Just like the NH2. Now the last one is kind of weird, right? So we have our weak activators here. Because the CH3, like toluene, doesn't have any resonance in terms of they're not going to donate electrons down or withdraw electrons out through delocalization. They don't have any p orbitals. What we're going to do is we're comparing an ortho mechanism, which is a lot like the para mechanism. You're going to see that these are the same. You can draw out the para one for yourself, and you'll see you get the same structures. But if we go ortho or para, the electrophile is going to put a positive spot here, which is a tertiary carbon, here, which is a secondary carbon, and here, which is a secondary carbon. Now, if we add meta to something that has an alkyl group, we're going to see that if it goes meta, we're going to have a secondary carbocation, a secondary carbocation, or a secondary carbocation. So that should not be as stable as the other intermediate, right? Where this one has a tertiary carbocation as part of its resonance structures, part of its delocalization, versus down here, we only have secondaries, right? They're all secondaries. So that means that if you were to look at what's going to go faster, right? So you have toluene here. And let's say toluene, we're starting off at this level, and we're going to go down in energy to either the ortho or the para. Those are going to be about the same. There will be slightly different, of course, but roughly the same for the sake of this. So your product, I'll just write product. The idea is that the green one, right, if you go ortho or para, that's going to be lower in energy than the blue one, because that one's going to be secondary, 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 and the green one is going to be tertiary, secondary, secondary. So if you're just looking at these two paths, which one's faster, it looks like, and forgive my humps are not exactly proportional, but the point is that it's going to be easier to go the green route. The green route is faster. So these tend to be ortho-para directors. The ortho-para mechanism is going to be faster. Because that intermediate is lower in energy, because you get a carbocation on a tertiary carbon, in meta, you just can't do it. Neither of those positions do. So the meta reactions are just slower, so we don't see a lot of meta additions for these electrophilic aromatic substitutions. So let's go back and let's add stuff to these, right? I'll just fill this in real quick, right? We're talking about things like OH or OR, NH2, stuff like that, right? Things that had lone pairs. Alkyl group, so just CH3 or whatever your R group is. The halogens, so, chlorine, bromine, etc. Or things that have pi bonds at that point of attachment, or are fully positive, or something like that. If we go back to those previous slides and added what we just talked about, these strong activators, these were ortho-para directors, right? We said they donate electrons in, and those ortho and para spots became partially negative and therefore attracted the electrophile. I just on the previous slide did alkyl groups. We said that those were also orthopara directors because their intermediate has a tertiary carbocation in there, and that's going to be a lower energy intermediate and therefore a faster electrophilic aromatic substitution. For the deactivators, we saw that we got positive charges in those ortho and para positions, or in other words, places that are going to repel that electrophile. So we don't want to have a positive next to a positive, so it's going to repel and leaves only the meta positions that are as an option. And then lastly, halogens, because they have a lone pair, they also are ortho-para directors. So you want to look at these categories, these strong activators. They're always ortho-para directors. Weak activators, they're ortho-para directors. Strong deactivators are the meta directors, and weak deactivators are the ortho-para directors. Now, if I'm gonna apply that to some things, right? The idea here is that you want to look at whatever you've got, right? So in this case, I've got an acyl group. I see there's a pi bond at this point of attachment, so I know that this is a strong deactivator. And I know that my strong deactivators are meta directors, which means it's going to direct here or here, right? That's its meta positions. What am I going to put there? Apparently I'm doing a bromination, so I'm going to put a bromine in one of those two spots. And now it doesn't matter which of those two spots I put it in because it's symmetrical. I'm just going to draw that one. But it could have been the other meta spot. And so it doesn't matter what you add, and that's the point of the second one. It's not going to matter what you add. It's the thing that's already on there that is the director. So it doesn't matter if I did a bromination or a fructose acylation or a sulfonation or a nitration or whatever. The next thing is going meta if this is my starting material, right? If this is my starting material, the next thing you add, no matter what it is going to go meta. So why don't you take a second to pause, see if you can do these last four real quick, and then I'll come back and we'll solve them together. So let's look at this one, right? It's the same thing. It's still that strong deactivator. So I know it's still a meta director. And now I'm doing a sulfonation, so I'm going to get kind of the same product here. I'm going to draw the skeleton, but I'm just going to put a sulfonic acid there instead, the SO3H. And again, I could have done the other spot right down here. Either way, same thing. For the third one, it looks like this, right? I know a lone pair wasn't drawn on there, but I know there's lone pairs on there. I know that this is a strong activating group, which is an ortho-para directing group, which means I'm going to go para or I'm going to go ortho. As long as the group that's already on there is relatively small, you're going to get similar amounts of ortho and para. As soon as that group gets really big, para tends to predominate just for steric reasons. So I'm just going to draw, I'll draw both products. I'm going to draw the para product first. So I'll draw it opposite. How many carbons? 1, 2, 3, 4. 1, 2, 3, 4. And I'll draw some ortho product. I'm not going to ask you to tell me what like the product ratios should be. I just want you to know if they should be major or minor and what's reasonable, right? Like you should not draw any meta for this one. You should draw the ortho and the para product. Because what's going on here, right? This is a good time to talk about it. The para position is more stable just because you have more room, right? There's more rooms between this acyl group and the group that was already on there. So that's the advantage of the para position. The ortho position, right, obviously is going to bump into that group, but there are two ortho positions. So even if it's half as likely to add compared to a para, there's twice as many, so it ends up being equal-ish. You know, it could be 50-50, but like 60-40, 55-45. Oftentimes, if that group that's already on there is relatively small, the fact there's two orthos sort of equalizes the fact that the para position is just better in terms of sterics. So draw both products. If I'm asking for the major products, I want you to draw both of them. Now that's going to be different for this next one here, right? So here I have an alkyl group, which we just said is a weak activating group and is also ortho-para directing. So here's its ortho positions right next to the T-butyl, and here's the para position on the opposite side of the T-butyl. Now, the big thing with this, right, is T-butyl is huge. It's like one of the biggest groups that you can put on something. It takes up so much space, which is why for this one, I am not going to really draw any ortho product as a major product. Because the T-butyl group is so big, I'm going to just draw my nitro group opposite of it. That should be my major product. I may get some ortho, but probably very little, relatively little. And so just be mindful of, if you do have an ortho-para director, if it's really bulky and big, pick mostly the para product. If it's small, you're going to get a mixture of ortho and para. And then lastly, I wanted to show you this one because you may see some that have two groups on them, right? So like if I look at the methyl group, that is a weak activator, just like the butyl group was. That says put something ortho-para. So for the methyl group, ortho is there, para is there, and its other ortho is already blocked because there's a bromine. So the methyl group is saying, well, put it there or there. However, if I look at the bromine, which is a weak deactivator, the weak deactivator is also ortho-para directing. It's saying, well, okay, put it here, that's its ortho, or here, it's para. So it kind of looks like, well, all of the positions are being selected for, so how am I going to decide? What you do in this case, when you have two groups like this, is the most activating group is the single director. So the most activating group is the director. So for me, that means that my ortho-para group, since that's a weak activator and weak activators are more activating than weak deactivators, I'm just going to listen to it. So I'm going to put it either in this position or this position. Those are the only two positions really that are going to be viable. So that means I'm either going to have CH3, bromine, and chlorine, or bromine, CH3, and chlorine. And between the two of these, this one definitely looks major to me because the chlorine is going to have more space. This would be the minor one because you're cramming all of the groups together. So if I was asked for one product, I'd pick that one. So this will take a little bit of practice, right? You want to know that chart that I just showed you. You know, what are the ortho-para directors, what are the meta directors? But as you practice this, this gets easier and easier and easier, and you just need to do the work. Just do the practice, you'll be fine. So happy studying, good luck, have a great rest of the day.